Let it be. I can.
Yeah,
You started?
Yeah.
Okay. Good afternoon. I guess if you have any questions, you can write in the chat. Good afternoon. Spectrum of a ring. Yes, of course I can. So, so if you have a ring R, spec of R by definition is set of all prime ideals. Right? What are the P is a prime ideal of R. Yeah. So spec of R. So why is this important? There are, geometric reasons why this is important, but let me not get into geometric reason. But I'll tell you some, because if I have to say about geometric reasons, I need to say a lot about its topology, etc. So here, maybe I'll give a brief about this. So let's look at some nice examples. For example, if you take any R as a PID, okay. Yeah, I hope you are able to view things. Let's see. Yeah, let's look at one important example. R equal to Cx, and I'll take another example. R equal to Cx. So in this one, we know exactly what are the prime elements of Cx. Prime is same as irreducible. What are the irreducible elements of Cx? So you have 0 is a prime ideal, and other than that, you have ideal generated by x minus a, where a ranges over all complex numbers. Right? This is the I should not write equal to, I should say then this is spec of R. Now this one can see this as a topological space. So what is meant by a topological space? I hope you have done a course in topology, basic course. So it's a set with structure defined on it, structure defined using open sets or closed sets. So here on spec R, you can define a closed set X in spec R is closed if X is equal to V of I. So I'll define what these terms are. V of I, where I is an ideal and V of I is set of all prime ideal containing I. Okay. Now, if you take in the case that we are looking at that R equal to Cx, every ideal is generated by every ideal is a principal ideal, and it is generated by some. Let me write this as ideal generated by Ax. But Ax is a polynomial in Cx. So Ax, I can write it as, it has a decomposition into powers of primes. Like I can write this as P1x power alpha 1, etc. Prx power alpha r. Okay. Now, what are the prime ideals containing I? Prime ideals containing I are, so again, this follows from one of the exercises you might have seen already, that an ideal A is contained in ideal B if and only if B is equal to, A is equal to some alpha times B for some alpha in R. This is in general for any ring. Now, or in other words, when you are in a PID, we can say that this happens if and only if B divides A. Now, this is PID, or you can, in when you define the division in this way, you can say that this is same as B divides A. Now, in this case, let's come back to our situation. When do you say this is, what are the ideals containing I? Ideals containing I are, using this, it's nothing but the factors of X. But now we are looking at ideals, not any ideal, but we are looking at prime ideals containing. When will this ideal ideal generated by a factor become a prime ideal? If it is generated by an irreducible element, which means it is the prime ideals that contain Ax are nothing but ideal generated by P1, ideal generated by P2, etc., ideal generated by PR. So what we are seeing now is that any closed set in Cx is nothing but of the form. So if I take any ideal I, V of I will be of the form P1x, Prx, right? Now, in this topology, any closed set is of the form P1x, P2x, Prx. Okay. An open set in Cx is nothing but in this topology. So this is called a Zariski topology. If you do not want to get into that, but you can just accept it as it is. Okay. Yeah. So therefore, every closed set is finitely many elements. Therefore, every open set is of the form that its complement is closed. Complement is finite. There is a very specific name for such a topology. It is called cofinite topology. So the topology defined by this closed set, of course, I have skipped a lot of details in this, that you need to prove that this satisfies all the properties of a closed set in a topology. All these things need to be done. That I leave it to you to do at home. But then the spec with this topology is nothing but cofinite topology on Cx. Now this topology plays a lot of role in studying the geometry of objects. When you take, instead of Cx, you can look at Cx1 up to xn, and with the same kind of topology, I look at spec of this ring and define the topology using closed sets, that any closed set is of the form V of I, where I is an ideal in R and V of I is nothing but prime ideals, collection of all prime ideals containing I. Okay. So this is called Zariski topology. Now, it will be a good idea to look at what is Zariski topology on Rx, okay, and Zx. That I'll leave it to you as an exercise. Okay. So this is what a spectrum of a ring. So this is a spectrum in some nice situation. Okay. Now, what more do you want to? Swaroop asked, can you please discuss about spectrum? So what more do you want? Like, if there is some specific question in mind, you can ask. Otherwise, we can move to some other question. So this is okay. Let me say one more thing. See, if you have a ring homomorphism from R to S, okay, phi is a ring homomorphism. Okay, and if P is a prime ideal in S, then we know that phi inverse of P is a prime ideal in R, right? So this naturally defines a map, we call it phi star, from spec of S to spec of R. Okay. Now we have defined the topology on spec of S. We have defined the topology on spec of R. Okay. So these are, phi star becomes a map between two topological spaces. So now you can think about this question. Is phi star continuous? Okay. So this is something to think about. Well, simple and semi-simple Artinian rings. We are, see, this is a commutative algebra course. In fact, when we talk about simple and semi-simple rings, they are most often non-commutative. So I would say we will not get into simple, semi-simple rings in this course. You can, it would be good if you can stick to the questions related to the course, okay, regarding whatever we have done so far in the course, something related to that. So kindly stick to these questions from the topics that we have discussed in the course so far. Okay, so I have gotten a printout question. Yeah, I think Neha Kumari has asked this question. What is the significance of Nakayama lemma? Okay, so let me. Oops. How do I remove this? Oh, sorry. I think I was looking at different. Okay. So, what does Nakayama lemma say? Suppose I have uh, module R module M. R is commutative ring with identity. M is finitely generated R module. Okay, and N is a submodule of M. Okay. Yeah. Then, so R is local, RM local. Okay. M finitely generated R module, and N is contained in. Okay, so one can state Nakayama lemma in more general setting, but let me stick to this when since we have to. I'll come back to Dinesh Kumar's question. But let me complete this. Okay. So, what does the Nakayama lemma say in this one? If n plus mm is equal to m, then n is equal to m. Okay. So the significance of this is, the first one I think you have uh, seen in the class itself, that look at this m mod mm. This is a vector space over R mod m, over R mod m, right? Now m is finitely generated, therefore this is a finitely generated vector space, which means it has a finite basis. So let's take x1, I'll use x1 bar, xn bar, be an R mod M basis. Of M mod M. Now, Nakayama lemma immediately tells me that this x1 to xm, this is a minimal generating set for M. See, this is important, sorry, not M here, this must be, this is a minimal generating set for M. This is a very important concept. There are a few things here. One is that given a module, how do you try to find a minimal generating set? Okay. And the number of minimal generating sets. So if you take a local ring finitely generated module over a local ring, Nakayama lemma immediately says that you take any minimal generating set. Okay. You start with any minimal generating set, the number is going to be the number of elements in the minimal generating set is going to be equal, right? It's very close to what we see in the case of finite dimensional vector space for fields. This is in general not true. For example, if you don't take local ring, like for example, you take Z. This is a minimal generating set for Z over Z. But this is also a minimal generating set for Z over Z. So if you are not in local ring situation, this result is no longer true. But in the case of modules over local rings, Nakayama lemma tells you that number of minimal generating set. You take any minimal generating set, its cardinality is uniquely determined. Okay, that's one of the most important applications of Nakayama lemma. Okay, and this is used heavily even in research, like in our research that I'm doing even now, like even in a paper that I have written last year, we use this to say that this is a minimal generating set. Looking at the number, we say this has to be a minimal generating set. Okay, so this is a very important aspect. Now coming to exact sequences. So if you have this, m to n to, let me write this as t to 0. This is one of the most important exact sequences. This is called a short exact sequence. So here, the importance of this short exact sequence is that if you have information about m, you can get a lot of information about n and p, and vice versa. If you have information about n and p, then you can get information about. So this is one important aspect of short exact sequences. Now there are more exact sequences called exact sequences. Start with, and I'll give you one example. If you have a module M, okay, if it is finitely generated, then we know that there exists a map from Rn to M. Okay, there is a surjective map, which means this is a this is an exact sequence. Okay, where this is the maybe I'll call this D naught. Okay, maybe I'll call this Rn naught. Now this has a kernel. Let me call this kernel K naught. Now, in certain circumstances, this K naught becomes naturally it becomes a finitely generated module. When this is a finitely generated module, I have a map. Let me call this Rn1 to K naught. Okay, and as a composition, I have a map from Rn1 to R naught. Okay, so let me call this. So this is the surjective map from Rn1 to K naught, and this is the inclusion map. This is the inclusion map. This is the surjective map. So composition of these two, I'll call this as D1. Let's say. Now this has a kernel. I'll call this K1. And again, when this is a finitely generated module, we have a map from Rn2 to this one. And composition, we call this D2. You can keep doing this. So when you look at finally what we get is an exact sequence like this: Rn0 to Rn1 to Rn2 and so on. This is called a minimal free resolution. So minimal this is called a free resolution. This is minimal in when some nice conditions are satisfied, but it's okay. This is called a free resolution, and again, a lot of properties of M one can, I mean, basically this sequence resolves M. Rn0 and this map tells you how complicated the relations are among the generators of M. And then this map tells you how complicated are the relations among the relations, and so on. So therefore, this gives you, I mean, this basically, looks into the structure of M in a lot of detailed manner. Okay, so this is called a resolution, and this is very important. These numbers are very important. Even now, for an arbitrary module, even in very nice case like polynomial ring, in very nice situations, module is very nice. Even then, these are still, there is no unique formula to compute or unique method to do this. Even now, people are doing research on, exploring or, understanding these numbers and these maps from a given module and idea. Yeah, so the third question from Neha is that I'm having problem in understanding commutative diagram of exact sequences. Yeah, so I mean, see, the problem is unless you tell me where you are getting stuck or what exactly the problem is, it's difficult to solve it. Okay. So commutative diagram of exact sequences. So okay, we don't need to worry about 0. You can even have ni, ni minus 1 to ni minus 2 and so on. Here I have mi to mi minus 1 to mi minus 2. If you have, sequence of homomorphisms like this with maps such that you start from here, come here and come here, or reach here using the other path, this way, this way. Either way, the end result must be same. That is, in each of these square, if this happens, then we call that this is a commutative diagram of exact sequences. So again, using this commutative diagram, if you know about certain maps, and if you know about some of the diagram modules, then one can talk about, or understand more about other maps and other modules. That's basically the application of this, and it comes in specific situations. For example, if you have okay, let me if you have like this, if it is 0 here and 0, this is called a 5 lemma. If you have sorry, this is the application of 5 lemma, in fact. So one can say that if these two maps are isomorphism, then this is an isomorphism. Okay. So there are a lot of properties that one can derive using short exact sequences, commutative diagram of exact sequences. Unless I know exactly the problem, I cannot really tell you how to I don't know how to solve your problem. Okay. Okay, so now let me look at some other questions that is being given here. So first question from Dinesh: when is car Hausdorff? Okay, so that's an interesting question. So let me take a new page here. Okay, so see, if you look at say, for example, Cx. Okay, what is the topology here? We have said that in this case, open sets are complement of finite sets, or closed sets are always finite sets. Therefore, the complement, open sets are all always complement of some finite set. Okay, but then there are infinitely many prime ideals here. Okay, so if you take any two open sets, they will always intersect, right? Now, in the case of Rx, I guess you can guess the result. Or more generally, if you take a PID, and apply Zariski topology on spec of R, that will be any closed set is a finite set. Therefore, the open set will be complement of a finite set. And if your PID is large enough, then you will always have intersection between any two open sets. So, and if your PID is large enough. Okay. Now, since you have asked when is it Hausdorff, let's look at. So one possibility is that you don't have enough finite sets. You don't have enough elements in spec R. What are the ideals that you know where the spec R is small? You have only very few prime ideals in a ring, right? One is if you take a field, the only prime ideal is 0. So it is a discrete topology. There is only nothing there. If I take R, let's look at one example. I'll give one example and then you can think about it, think about more examples in the same direction later. Z6. Okay. Z6 will be a little, okay, let me take Z30. Okay. What is spec of R here? Spec of R is ideal generated by 2 bar, ideal generated by 3 bar, ideal generated by 5 bar. These are the three prime ideals of Z30. Okay. Now, is this, I mean, what kind of topology do you think spec R has? It's a finite set. So whatever topology you apply on this, if it is a topology, then it has to be, I mean, either in discrete topology, which is not. In this case, we know it is not in discrete topology. But in this case, it is a discrete topology. So therefore, if I take any singleton, it is going to be open set, right? Because if I take this bar, why is this open? It is complement of this one, this set, right? It's the, this is equal to complement of this one. But what is this? This is, if I take the ideal generated by 10 bar, ideal generated by 10 bar, then the ideal containing the ideal generated by 10 bar are nothing but 2 and 5. Therefore, 3 is a complement of this one. So any singleton is open here. 3 is one such example. You can take any of them. Therefore, this is discrete topology. Therefore, you take any 2 points, you can separate them by open sets. Therefore, this is an example of a Hausdorff spec R. Now, try to see if you can construct an infinite spec R with Hausdorff, which is Hausdorff. Okay. Okay. So now let me get to the next question. How to draw a picture of spec of a ring? So this is yeah. So the picture is you have to represent the prime ideals using graphs. Okay. I mean, say curves. Okay. So that's how you basically draw pictures of spec of ZX, RX, CX. What is I mean, in see, you can, okay, so I'll tell you this. You can relate an ideal with its zeros in Rn. So that's one way that you can do. So you have, for an ideal I in, suppose you so let's look at kx1 up to xn. Okay, and look at this is okay, z of I is set of all a1 up to an in kn such that p a1 up to an, this is 0 for every p x1 up to xn in I. Okay, now if your field k is nice, then there is a very nice correspondence between I and zi. Okay, so this is another way to look at spec of I. Look at points containing ideals containing I, and look at how that branches out in zi. This is more geometry. And if I can do some hand waving here, but then if I need to write and give a proper explanation, it requires more time and more material. So we have a nice algebraic motivation for localization. You mentioned the geometric motivation as well. See, again, any geometric thing, I will need more geometric tools to say more. It's kind of difficult to explain it in such a short period. If you take up, see, if you do a algebraic geometry course, all these will be very clearly seen there. Okay, so localization. Okay, I will give you some glimpse of the localization. So this is, for example, suppose I take this. Suppose I have, I take a curve, or C is a curve in, let's say, Kn. Okay, curve, or some. So I will think of C as zero, zero set of a collection of polynomials. So this is contained in K power n. K, you can think of K as C or R. So I will write this as kx1 up to xn. So now there is a concept called coordinate ring of C. The coordinate ring of C is given by x1 up to xn mod I. So this is collection. Let me call this collection zero set of a collection. Let me call this S. So ideal generated by S. Okay. This is called coordinate ring of C. Sometimes denoted as K of C. Now, if I take any maximal ideal, if M is a maximal ideal containing or no, so okay, so let A be a point in C, okay, on the curve. Let M be maximal ideal generated by x minus a1, x1 minus a1 up to xn minus an. So let me call this ma. Okay. Now a c localized at ma. Okay. So what is kc localized at ma? I'm looking at s. Okay. I'm using s here for. Okay. So let me use t here. T as k x1 up to xn without this ma, and this is T inverse of kc. Okay. Now, this, if you look at this I mean this collection, this ring here, uh, every element looks like f by g, where g is in inverse. Okay, and the you know here g is a very nice polynomial in the sense that g is a polynomial gx not xn. Now you look at any point in C, and if okay, this is if B is a point in C, then G of B must be non-zero. That's because, see, the C is basically collection of all zero sets of this, this collection of polynomials. So the ideal of C is the set of all polynomials that vanish on this point, on all points of C. So now if I take a polynomial outside that collection, it is going to be non-zero. Therefore, this this is collection is set of all f by g, where f and g are what are called, f is a polynomial. F is, of course, you can think of it as a map from kn to k, f and g. But then f by g makes sense outside C. Therefore, this is a in C. Therefore, this is called ring of regular functions on C. So, this is one of the geometric aspects of localization. That if you look at this, if you look at this ring, okay, looking at the algebraic behavior of this ring, you can say how good the point A is, whether it has singularity at that point or is it smooth and so on. So geometric property can be revealed using this algebraic behavior. Okay, so that is one important aspect of the geometric aspect of localization. Algebraically, there are a lot more, of course, in geometry also, but this is one of the situations. I'm having difficulty in computing the tensor product of the z module q mod z with itself. I mean, having difficulty in the sense, I mean, what it's not clear what is that you're expecting here. So your q mod z, what is it? You want to say what q mod z? Tensor product of q mod z with itself. What about this? Like I am not able to see what kind of difficulty you're facing. It's not clear to me what kind of difficulty you are facing. If you can be a little more precise on your problem, then I can try to resolve. See, and like for specific problems, you can post in that form also in that forum, and either me or the TA Rajiv, either of us will respond as early as possible. So, I mean, and moreover, like it's difficult. See, when we are sitting face to face, it's easy when you say you don't understand this. I can ask you where is the trouble. Like you can start at some point and then find out where exactly you are getting stuck, and then I can resolve. But in a forum, you should write more specific questions. Like I don't understand this point. I should say something like that. Then it should be easy to look at how the elementary tensor look like so that I can describe the elements here. Elementary tensor, well, I mean, I don't, so okay. P by Q R tensor, R by S bar. This is how the elementary tensor looks like. But in this one, what exactly something that you're looking for? That's again, say for example, okay, so let me say if I have 3 by 2, okay, 3 by 2 bar tensor 1 by 3 bar. Okay, this one I can write it as 1 by 2 bar, and so I can take 3 the other side. So it becomes 3 by 3 bar, but this becomes 0. So this will be 0. Okay. So these are, these are some basic rules in, the elementary tensor. So tensors like this will become 0. Others will remain as, like a free element. It will be a free generator of the entire, the module. Like that's how we constructed Q mod Z cross Q mod Z. And then we take the free module over this and then mod out using the relations. Okay. So like elements like this will become 0. Otherwise, it will remain as it is. Zero set will always be a continuum. What is that? Continuum means, I mean, will it look like a graph kind of thing? Is that what you have in mind? I mean, that will depend on your field. Okay. For example, if you take a finite field, it makes sense. All these make sense, even in finite field case. In that case, you can't draw it like that. But it'll, algebraically you can make out what it is. Yeah. Any other question? Uncountable, we cannot really say. Depends on your field. That's what I said. Field, or the ring that you're basically looking at. That it depends there. Null stanza is applied when your field is algebraically closed. Okay. So I mean, if your field is algebraically closed, it is always infinite. But for the to see a connection between the zero set and the ideal, I mean, you still can do that without even without null stanza. You can see. I'm not saying null stanza holds, but what I'm saying is you can understand the geometry of or the connection between the the geometric set in Kn and the algebraic set, the ideal, even in that case. Tensor product is heavily used when we have to, like when we want to understand what are the say for example, if I want to mod out certain parts of a module. Okay, say for example, if I have, suppose your module is m or sorry, m directs some n mod im in, okay, or for example, m directs some n and I is equal to annihilator of n. Okay, now if I call this, so if I take I tensor m directs some n, okay, then this part goes off, right? You just have I tensor m, which is im. Okay, so I mean, this is just, so this is one way to use tensor to eliminate some portion. And then there are a lot of other applications, like when we so in your class you have seen that tensor is not left exact, right? You can have this is exact, but m tensor okay, so here let me use m tensor p to n tensor p. This need not necessarily be injective. So when some module satisfies the property that this is injective, then this module P is called a faithful module. So when module is faithful, you can, there are lots of nice properties that holds. You can, understanding the structure, to understand the structure of P, there are lots of ways. Okay, so even using tensor product and even with using other tools. So whether a module is faithful or not can be found out using tensor products. Okay, so that's one of the uses tensor product has. And in the higher algebraic aspects, there are a lot of them. Not all of them I can explain now, because to explain this, it requires a lot of tools. So these are a couple of them that you can probably see or accept at least. That's okay, Swarup. The only thing is that I am unable to answer all of them because of the limitations that we have. It would be interesting, after doing a course in commutative algebra, a natural follow-up is to do a course in algebraic geometry. And there you will see a whole lot of commutative algebra getting applied and a lot of interesting things happening there. So if you are interested in geometry, the next step is to do the course on algebraic geometry. Any other questions? Yeah, I don't see any. Okay, so you can make an announcement, or broadcast broadcast message to them saying that it is. Oh, okay, 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 okay. Yeah, yeah, a lot of connection, algebraic geometry with complex analysis as well. One has to be, a lot of. Okay, I think it's time to wind up. We will